All right, in section 10.5, we'll be taking a look at tangents. So tangent, remember, is like if you're having a conversation and the conversation is here and someone goes off on a tangent, they start talking about something completely different away from the conversation. So basically the same idea for circles. A tangent is something that touches the curve and then goes away from it after that. So this is all from day one of the notes, just reminders. Circles can intersect in 2 points, 1 point, or no points. So when they intersect in 2 points, their centers could be separate, or their centers could be such that one center is inside of the other, or that both centers are inside of each other. And then if they touch in 1 point, that means the two circles are tangent to each other, so because they only touch at 1 point. Those circles could be exterior to each other or interior to each other. There's 2 ways to arrange that. And then finally, no intersection could be 2 completely separate circles or 2 concentric circles or even a small circle inside of a big one that's eccentric. Looks like an olive, I guess. So there's 3 ways we can kind of arrange those. They're either the center of the inner circle is inside the outer one and concentric, or inside and not concentric. And then these are just completely separate. So other vocabulary reminder from day one, secant is a chord that we extend beyond the limits of the circle. So if I have a chord and then it keeps going and extends outside the circle, that's a secant, whereas a line that only touches 1 point, like this one, is a tangent. So secants and tangents both kind of pass by the circle. One of them intersects twice, one intersects once. So a tangent line intersects at exactly 1 point. We call that point the point of tangency. You can also have a point of tangency between other objects, like you saw a circle and a circle had a point of tangency there. A line is tangent to a circle if and only if it is, I'm guessing, perpendicular to a radius drawn to the point of tangency. So if that's not what goes there, that's what we need to know anyway. So the important thing about tangents is they're always perpendicular to a radius. So if you think about this line passing by, we've already established that the minimum distance between a point, like point P, and a line is a perpendicular intersector, right? So we did that with distance from a point to a line earlier in the year. So if I want to know whether this is the minimum distance, I can kind of just look at the circle and the point of tangency. I'll use this bigger one. So if I go from C to anywhere else on this segment AF, or line AF, ray, I guess, there's one arrow, whatever. If I go from C to anywhere but E, I have to travel a distance equal to the radius plus a little bit more once I get past the circle. No matter what way I go, I have to go a little bit further than the radius. So we know that C to E is the minimum distance, and we know that a minimum distance between a point and a line is always perpendicular. So there's more rigorous proofs of that, but we've kind of already know all of the building blocks, so I think we can just understand that those are perpendicular and move on. All right, so example 1, tell whether the line or segment is a radius, chord, diameter, secant, or tangent. So it says best classified, so that would mean the most specific name. So for example, ED is a chord, but it's more specifically a diameter. A diameter is a special kind of chord. So if they ask for ED, which they do right here, they say line ED, that's strange, that should be segment DE, and that's going to be a diameter. Then they ask DC, that's a radius, it connects the center of the circle to the edge of the circle. BD is connecting a point on the circle to another point on the circle. It's a segment, so that's a chord. DE, like we said, is both a chord and a diameter, so that's our most specific name. AE, they say line AE, so that's this whole thing, including an arrow that way, is going to be tangent to the circle because it only touches at point E. So E, remember, was called a point of tangency. And then AD, line AD, is going to be a secant because it intersects the circle at B and D, so it's not tangent. It has more than one point of intersection. Point E, oh, that went here. Point E is point of tangency. I didn't realize they were going to ask us that. Okay, a line, ray, or segment that is tangent to two coplanar circles is a common tangent. So if you see the phrase common tangent, that just means that that object, that line, segment, or whatever, is tangent to multiple circles. They'll usually tell us which one. So they would say it's a common tangent of like circle A and circle B would be this line. So here they want us to draw all the common tangents. So with two separate circles like this, there's a number of ways we could draw it. So we could have a line that kind of encompasses both. So like here would be tangent above both of them. Here would be tangent below both of them. But we could also draw tangents that pass between the two circles. So this one is going to be above, we'll call this circle X, and below circle Y. So basically like passing like this. I know it's not perfect, but just pretend. So I go over circle X and under circle Y, or I could do the reverse. I could start from underneath circle X and go up and above circle Y. So basically there's four options for my common tangents when I have these two circles that are separate like that. If my two circles are tangent to each other, I lose the ability to draw these green lines that go between the circles. So here I would have a tangent line that way and a tangent line that way. So I can't have a line that goes above one and below the other, but I could technically have a line that splits perfectly between these two and only intersects them at that one point. So if you zoomed way, way in, that would be like the two circles are touching right here, and that line touches that one point. And it's at the perfect slope that it passes between the circles without intersecting either of them again. So there should be a total of 3 there because this above and below line kind of become the same line. C, we have passing above both and below both. Now we can't do anything between the circles because if I pass anywhere between them, I'll be a secant to at least one of the circles. So here is just 2 options. And then finally here we have 1 option. So just passing above both of the circles, touching them at their point of tangency. So these two both are touching at the point of tangency. Point of tangency. So this one coming through the middle here and this one passing over the top are intersecting at the point of tangency. So if the circles are tangent to each other, there's a line that goes through that point of tangency. And then if the circles are basically outside of each other, like here, we get 2 lines of tangency that pass above and below them. When both of those are true, we add it together and we get 3 lines. And then if we separate them further, then from then on we have 4. So we have 1, 2, 3, or 4, depending on whether the circles are tangent gives us 1, and then whether they're separate outside of each other gives us 2 more, maybe 3 more. Well, it gives us 2 more, and then here separating them further gives us those 2 additional ones. Okay. I'm trying to think. I can't get it. So you get it. The picture describes it. Okay. So is AB tangent to circle P? In order to know that, we need to know if this angle is a right angle, because we know that a radius, PA, and a tangent, AB, need to be perpendicular. So when they say this thing, that's like asking, is segment AP perpendicular to segment AB? If so, then it is tangent. So 8, 15, 17 is a Pythagorean triple. That means we know that it is a right angle. So yes, it is going to be tangent. Here we have 11, 14, and 5. That's not a Pythagorean triple, meaning it's not a right angle. We can confirm that with a Pythagorean inequality and do 25, that's a squared, plus 121, that's b squared. And we would compare that against c squared. I forget 14 squared, that's 140 plus 56, 196. 196. So 196 is too big. C squared is bigger than a squared plus b squared. So this would be an obtuse angle, not a right angle. And we don't actually need to know if it's obtuse or acute here. We can say no just because with nice even numbers like 5, 11, 14, if we know our Pythagorean triples, we know that's not one of them. So if they don't bring in any decimals or radicals, we can easily recognize a set of 3 integers as being a Pythagorean triple or not. All right, example 4, in diagram J is a point of tangency. Find the radius of circle G. Okay, so we have our tangent JH, so we know that segment JH is perpendicular to segment GJ. So that gives us a 90-degree angle here. And since we don't have any other angles, we're not using trigonometry here, we'll be using the Pythagorean theorem. So we have x and x plus 8 and 12. X plus 8 looks to be C because that's across from the right angle, and then x and 12 are A and B. So squaring those out, we get x squared plus 144, and we need that to be equal, because we know this has to be perpendicular, to the square of this one. So x plus 8 squared, remember when squaring a binomial, we get a trinomial, so we get x squared. In the middle, we get 8x twice, so plus 16x, and then 8 squared is 64. So we would need to solve that. First, we get rid of the x squared, so we don't actually need to do a quadratic. Then we have subtract 64, we get 80 equals 16x, so x equals 5. That gives us 13, 5, and 12, so it does end up being a Pythagorean triple, so that's great. Note that just because this is a 12 does not mean this is 5, 12, 13, right? This could have come out to be some radical in some other number. It doesn't have to be a Pythagorean triple just because there's a 12 there. Okay. More properties. So if we have a point outside the circle and we draw tangents to the circle, there's always going to be 2 options. So we can make the tangent that goes above the circle or the tangent that goes below the circle. And if you rotate your view, obviously, I mean just to the 2 different sides, right? If I'm down here, I would go to the left of the circle or the right of the circle. The idea is from any point around the circle, you can always make 2 tangents that go past the circle. Okay, so when we do that, we know that the distance from A to B and C to B are the same. So a way to think about that is we have, basically if you connect D to B, then you end up with 2 right triangles. We know that these radii are equal because each AD and DC are both radii. And then DB is the same as itself by the reflexive property of congruence. So what we have is a 90-degree angle, a congruent leg, and a congruent hypotenuse. So by HL, we can say, HL congruence, we can say that these 2 triangles are the same. And then by CP-CTC, we could say AB is congruent to CB. So anytime we pick any point anywhere outside the circle, if we draw the 2 tangents, so if I draw the tangent here and here, these 2 are going to be congruent to each other. All right, so that means if we draw a polygon that circumscribes the circle is inscribed in the polygon, then we know that from each vertex of that polygon, we have 2 congruent segments that are going up to the circle. So then that would allow us to solve for missing pieces of those sides of the polygon. All right, here it says find the value of x. So we have, they don't state that this is tangent, but I guess we're going to assume it is. It should really be stated that these are tangent for us to be able to assume that. But anyways, we'll assume that this is a right angle because it's tangent. So we have square root of 4 squared plus 8 squared is going to be x by Pythagorean theorem. So we have square root of 16 plus 64, which is the square root of 80, which is 4 square root of 5, because that's 16 times 5. So this is 4 root 5. Over here we have, again, these are equal. So we have 4x squared plus 5x equals 6. I'm going to move that 6 over here and set it equal to 0 because we have a quadratic to solve. So I'm just going to try to factor it. So we have negative 24 for a times c, and we're trying to make 5 by subtraction. So we need a difference of 5. That would be 3 and 8. So I have 4x squared plus 8x minus 3x minus 6. So that's 4x times x plus 2 minus 3 times x plus 2. So 4x minus 3 times x plus 2. That gives me solutions of negative 2 and positive 3/4. Negative 2 isn't going to work, right? Let's see. So if we do negative 2, that would be 16 minus 10. That does work. Negative 2 is a valid solution. And if we do 3/4, that's 9/16 or 9/4 when we multiply it, plus 15/4, that's 24/4 equals 6. Those are both valid. Okay, so remember when there's an x squared, we need to check the solutions. Just because this is negative doesn't mean it's not valid. What makes it invalid is if a side of if a length in geometry is negative. We can't have a negative length, but we can have a negative x value. That's okay. So we end up with 2 valid solutions. So this section is talking about circumscribed and not circumscribed polygons. So in order to be circumscribed, remember that every side of the polygon has to be tangent to the circle. So this one, and this one are all tangent. Here, all of those are tangent. We talked about for quadrilaterals, we need the opposite angles to be supplementary in order for it to be able to be circumscribed. But here we have a rectangle. Even though opposite angles are supplementary, this still is not circumscribed because we're missing this point of tangency over here. So when you're dealing with this property about the equal distances, make sure that you're actually dealing with tangents. So for this rectangle, there are tangents. There's still things we can do where this point is tangent here and here. So we know that this length and this one are equal. This one is tangent there and there. So we know that length and that length are equal. But we can't say anything over here because this segment isn't tangent. So this point over here doesn't have that special property. We'd have to draw this line, and now we would know these two are going to be congruent. But the way it's set up here, we can't conclude anything over on this right side. Same thing here, we don't have any pairs of tangent segments, and here we don't have anything tangent. So just be careful that you only apply tangent properties to tangent problems. Okay, so we have an example where a graphic designer is giving directions to make a larger version of a logo. And if we're going to take ABC circumscribed, the logo is circular, so I don't know what that means. Find the perimeter of triangle ABC. That's a strange statement this is making. Anyways, they want us to just solve for perimeter of triangle ABC. That we can do. So I know that from B, the two tangents are EB and FB. Those are congruent. So this is 7 from F to B. Meaning, taking away from my 10 here by segment addition, CF is 3. And from C, I see that CD and CF are the same because those are both tangent to the circle. That means this is also 3. Up here, A has 2 tangents, AD and AE. They're congruent, so we have 8 over here again. So just remember that it's not that we're like bisecting AB or anything. The focus is this corner, and as we project out from it, we get two congruent segments up to that point of tangency. So in total, we have a side that's 10, a side that's 15, and a side that's 11. So our total perimeter is 2636 feet. Hopefully simple enough. So then we have some practice. There's been a few examples we've already gone through. So there's really nothing new here. The two properties that we're using are this equidistant thing. So if we have a point exterior to the circle, we know that these are going to be congruent. Or if we have a single tangent with a radius, we know that they're perpendicular. We can also draw a radius as a auxiliary line. So if we need a radius and one isn't there, we can always add a radius as well. We can also find angles this way, although I don't see any problems here that involve that yet. So just like using number 4 as an example, if I draw a radius BH and I draw a radius HC, I know these are both 90. So the other thing that tells me is that angle A, so measure of angle A plus measure of angle H, that central angle, is going to be 180 degrees because they have to be supplementary when we've already used up these two 90s right here. So if I know this angle, or I know my arc measure, or I know my central angle, I can find the other two things. So let's say that measure of angle H was given as like 120 degrees. Then I know that measure of arc BC is also 120 degrees, and I know measure of angle A is 60 degrees. So knowing any one of those three measurements gives me the other ones when I'm measuring to a tangent point out here. So I don't see that. Let's see on the next page if they have anything with angles. Doesn't look like it. So maybe we'll cover that a bit later, or maybe it's missing in here. I don't know. Maybe it's here with angle measures. But to me, that is a property of tangents specifically because we're making, those two tangents at 90 degrees. So I'll include it in the notes here, probably do that in class as well. You may need to use trigonometry on some of these, perhaps, as it says round to the nearest tenth. So there's no angles. These should be Pythagorean theorem. We shouldn't need to round these. Anyways, you have these 2 pages to practice, so do those problems, make sure you got it down, and then we'll do our next section of notes.